Hello everyone, welcome back to ArcGIS channel. In this video tutorial, we will learn how to use various spatial and non-spatial models in ArcGIS Pro environment to examine the relationship between independent variables and dependent variable across geographic space. I will walk you through the steps of preparing the data, variable selection, understanding model settings, running the models, and interpreting the results. Our research questions are: first, to identify the most important and significant social vulnerability index variables that explain geographic variations of HIV prevalence in South Carolina, and then we examine the local association between these selected SVI variables and HIV prevalence in South Carolina using local models in ArcGIS environments. So let's get started. So first of all, I'm gonna create a new folder and call it 7_spatial models, and then open up ArcGIS Pro and create a new project. I'm gonna call this spatial models, and I'm gonna save this in lab 7 folder. Alright, so in the previous lab, if you remember, we obtained HIV prevalence data from county health ranking in South Carolina at the county level, right? So from map, add data, and then clustering, I think this one, HIV-SC, load it into ArcGIS. So this data had the HIV prevalence information in South Carolina at the county level. And also, if you remember, we obtained social vulnerability index variables from CDC in South Carolina at the county level. I think it was in lab number 2. If you go back, lab 2 SVI, here we had SVI for the year 2020. So let's add this data as well. Let's open up SVI attribute table. And as you can see, there are numerous fields for SVI variables, but we are just going to focus on estimated percentage of the SVI. So I'm going to just filter out the variables that I want, which are, for example, EP, all of the variables that start with EP, and also I need FIPS for joining this with the HIV prevalence. So there are multiple options. You can easily delete the field. So if you click on Analyze and then Tools and then Delete, you can delete the fields, and that's one approach. Another approach is that you can filter out the variables that you want. I click on this layer and then Data Design and Fields. So I am going to so first of all, I'm going to uncheck all of the variables, but I'm going to select FIPS. And also, I am going to select, let me sort the variables. I'm going to select the variables that start with EP. So all of the variables that start with EP, but I don't need the variables that are, for example, race variable. Okay, so for example, this is African American. And so I can, and also the age. So because these are the variables that I'm going to include in the model. So I'm not gonna include these variables because they are already have been included in another field, which is minority. So I am going to just focus on, for example, crowd, disability, group Q, housing burn. So I don't need the Hispanic or race information. Limited English, minority, mobile homes. I think this one is the housing structure. This one I think is for the another racial factors. This one, no vehicle to or, so I don't need that. POV, that's poverty. Single, I think single parent houses. So unemployment rate, uninsurance. I also don't want to get the age information, and that's it. So these are the variables that I would like to see. So I am going to save this file. So now if you open up the attribute table of this, you can only see this few variables that I'm going to use in my modeling. So I excluded the variables that were related to race or age from my model. I can also do the same for HIV. It's not that important because we don't have many variables, but I only want to keep probably, so let's look at the attribute table. I'm going to keep the name and also FIPS or GeoID. So GeoID, name, and HIV case and HIV prevalence. Okay, so from here, data design fields. So I am going to just select the name and FIPS, HIV cases and HIV prevalence, and also GeoID. That's a GeoID, name, and HIV case and prevalence. You can also keep county if you want. So save. So what happened is that if you open up the attribute table, I only have this variable. So GeoID, the data type here is text, and for SVI variable, the FIPS is also text. So I can easily join them. I can easily join, right click on HIV SC or SVI, and then join and relate, add join. So since the data type was the same for both, for FIPS was text, so I can easily join these two layers. So from HIV SC, I'm gonna select FIPS, which was GeoID, and for SVI, I am going to use FIPS. So if you click OK, and now if you open up the attribute table for HIV here, so you can see all of this information have been added to HIV prevalence data. So I have this one, HIV prevalence is my dependent variable, and all of the variables, the other variables except for FIPS, as independent variables. So I'm going to right click to make this permanent, export, and I'm going to save this in my lab 7 folder. I'm gonna call this HIV_SVI, and then OK. Alright, so now I can get rid of the other variables, and I have, this one is permanent now. I have the information about the HIV prevalence and the SVI variables, and also it included the length and area automatically. Since we have, I think, 15 or 16 variables here, we would like to select the most important variables because some of the variables are highly correlated, and we have to select only the most important and independent variable. Right, so we need to select Analysis tab, Tools, and then go to the Toolboxes tab, and here select Spatial Statistics, and then Modeling Spatial Relationship. So you can use ordinary least square model and try various combination of the variables, but I found this one, Exploratory regression, much more useful because it tests all possible combinations of candidates, explanatory variables, and also which is much more comprehensive than OLS, and also we can set some thresholds for collinearity, for normality of residuals, and so on. Let's select the exploratory regression. So here you need to specify what is the dependent variable, what is your independent variables, which I am going to select all of the variables, and the software will examine all possible combination. Okay, so I use this exploratory regression mostly for variable selection. So my input feature is going to be HIV SVI, the dependent variable is prevalence, and independent variable is going to be all of the variables that start with EP. All right. So another filter that you can set, if you click on search criteria, okay, so I'm going to say how many maximum number of the variables that I'm going to select. For example, I can set this to 5, or I can increase that, for example, 7. And minimum number of the explanatory variable, I can set this to 1, which is fine. So here, adjusted R square shows that what percentage of the variation of the HIV prevalence can be explained by these variables, okay? So the minimum adjusted R-square in the model, the final model, at least has to be 50% here. I can also increase that, okay? So I can set that at least I want the model explain over 60% of variation of the HIV prevalence in South Carolina. And also for the variables, we have to make sure that all of the variables are significant, and here is a significance level which is 0.05. So the good thing about this exploratory regression is that first of all it's tests all combination of the variables, for example from 1 variable to 7 variables. It has to make sure that the adjusted R-square in the final model is above 60%. All of the variables are significant, so at the p-value of the 0.05 or less, that's the maximum p-value. And also VIF, which stands for variance inflation factor. So it's more about multicollinearity. Normally the value is 7.5. So if the VIF for the variable is less than 7.5, it shows that the multicollinearity is low. But I want to take a more conservative approach, and I'm going to select 5. If the VIF is less than, or I can select the values like 3.5 or 3. So if the collinearity is less than, VIF is less than 5, so that is okay, but the maximum is 5. So JB test is used for normality of the residuals. Okay, so one of the assumptions of the linear regression is that the residuals should have a normal distribution. So the null hypothesis here shows that the distribution is normal, okay? But if p-value is less than 0.05, so it rejects the null hypothesis, which means that the distribution is not normal. The distribution of error is not normal. So here we said that if only select the models that their p-value for the JP is greater than this, which means that it cannot reject the normality assumption. So the higher value for JB p-value is better. Okay, so if it's less than 0.05, it rejects the normality assumption, but we don't want. So we don't want models that their residuals are not normally distributed. So, and also here, spatial autocorrelation, we don't need models that their p-value for a spatial autocorrelation is lower than 0.05, which means that the variables are highly autocorrelated. So we want something that their p-value is high. So the higher JB and the higher SA or spatial autocorrelation is better. Okay, so if it's above 0.1, it's okay, but higher value much better. So let's run this. Okay, so now if you click on view detail, first of all, among all of the variables that we have, like there are I think 15 variables. If I want to select one variable, so here it says that if you want to select one variable, minority can explain 67% of variation, right? Which is above 60%, the threshold that we had. And also JB is greater than 0.1, and also SA is greater than 0.1, and also VIF is less than 5. So it satisfies all of the criteria that we had, right? So that's why this model passed the criteria. So this model alone, just with one variable, which is significant as you can see, can explain 67% variation of the HIV prevalence, right? But now we want to explain more, right? So we add more variables. So it keeps this variable and adds more variable. As you can see, minority, minority, minority. So adds other variable. For example, M unit, I think, which is the percentage of housing in structures with 10 or more units. So which kind of shows the more densely populated areas. So this one also, if we add this, 3% will be added to adjusted R-square. And also if you add the crowded, overcrowded, or no high school diploma, I think. So this variable can increase R-square the most, right? But all of them pass the criteria. Why? Because all of them, the VIF is lower than 5, SA or spatial autocorrelation p-value is greater than 0.1, and also the JB is also greater than 0.1. So all of them pass this. So as you can see, all of them pass. So now let's add more. We add another one. You can see adjusted R-square will increase to 73%, 72, 71%. This model has the lowest VIF or multicollinearity because we are looking for the model that has lowest multicollinearity. And and also the p-value for the SI and also p-value for JB in general, and also it has the lowest AIC. So in general, this model has a better performance. So that's why the minority, M-unit, and limited English has been selected. So if we add another variable, so you can see none of them could pass this. So if you look at that, disability is not significant because we said that the p-value for the model should be less than 0.05. But so let's say that this is my final model, only 4 variables. And after 4 variables, you can see that when we add more variables, the adjusted R-squared doesn't change at all, right? So it doesn't work that we add so many variables, but it cannot explain more variation of the HIV prevalence. So I stop with 4 variables. I can also remove the disability, but let's now run the ordinal square model. If you click Tools and then select ordinal square, so my input feature is going to be HIV SVI, the unique field that I'm going to use. So probably I have to use a better unique field. Okay, so it doesn't allow me. So let me create a field that is integer. Okay, so I'm gonna add a field. I'm gonna call this FIPS2 and long integer, and here I'm gonna say that FIPS2 is FIPS. FIPS2 is FIPS. Apply and OK. So now if I select the ordinal square model, HIV SVI, the unique field, I'm not going to use the HIV cases, I'm going to use the FIPS2. So it's a unique field to identify the values and based on the FIPS, but the other one was based on text, so that's why it couldn't identify that. So it needs a number field. So the output, I'm going to just call this OLS, OLS1 or OLS, and dependent variable is going to be prevalence of HIV. The independent variable was limited English, minority, disability, and unit, right? And seems good, so I'm gonna here call this OLS, and everything looks good, and then run. Alright, so if you click on view detail, so here we can see the variables that we have selected. As you can see, the disability here is not significantly different from 0, okay, so that we couldn't reject the null hypothesis. The null hypothesis here states that all of the variables are 0, no influence, but here we were able to reject the null hypothesis with limited English, minority, and M unit. But disability is not, so we have to remove it. But let's look at the other variable, like VIF, all of them are less than 3. R-square, adjusted R-square is 73%. So let me, before explaining the other stuff, I can easily remove the disability. So I just wanted to show you that disability is not significant and we have to remove it from the model. So if you go to the history, ordinal square, and here I am going to just uncheck the disability and rerun. All right, so now again, if you open up the view detail, and you can see all of the variables are significant at 95% confidence level, and also the VIF or multicollinearity, all of them are less than 3, less than 5, so multicollinearity is not the issue in this example. And adjusted R-square is almost 73%, so this model based on these three variables, I can explain 73% of the HIV prevalence in South Carolina. AKK information criterion, so that is used for, the number doesn't make any sense, 565.2, but the lower value of AIC shows a better and more parsimonious model. So the model, if you have multiple models, you want to compare which one has a better performance. So we normally select the one that has a lower AIC. So FS statistics and also Walden statistics, they show the overall status of the model, whether the overall model is significant or not. As you can see, based on F and Walden statistics, the overall model is significant. So we also talked about JB, so which shows that whether residuals are normal or not. And as you can see, the p-value for JB here is not significant, which means that we accept that the residual has a normal distribution. If it was significant, it was less than 0.05, so you would say that the distribution of residuals is not normal, which is a very bad sign. Okay, so we have to make sure one of the assumptions of the OLS is that the residuals has a normal distribution. But how about the Ken-Kerr? So Ken-Kerr statistic, if it's significant, it shows that the relationship is not consistent. So it shows non-stationarity. Okay, so here the OLS cannot, so it shows that here we have non-stationarity because it was significant. The result is not consistent or constant, the relationship. So that's why the OLS, maybe we need to use local models to address non-stationarity. So now another thing is that here, if you go to the, I think, parameters tab, here there is a PDF file of OLS that we created. We asked for the PDF. So if you open up this PDF, here it shows that all of the variables are significant, VIFs are less than 3, and also we have the adjusted R-square, and also we have the AIC, and Ken-Kerr, JB, the overall status, and also you can look at the relationship between the dependent and independent variable, negative, positive, or almost negative. And here the residuals, you can see that the residuals almost have the normal distribution. But we can also check the from a statistical viewpoint. So we can also use global Moran's I to see whether the residual has a random distribution. Okay, so the residual should have a random distribution. So that is one of the assumptions of the ordinary least square. So how we can check that? If we search Moran's I here, spatial autocorrelation global Moran's I. So for the ordinary least square, generate report, but I want to check the standard residual or residual, doesn't matter. So I'm going to select the standard residual based on, so we already discussed this in the previous lab, fully discussed this. So if you haven't looked at that, I highly suggest you to watch that video about the clustering. So contiguity edges corner, I'm going to select this and then standardization of the row and then run. So if we get the outcome random, if the distribution shows random or not significantly different from random, so that's a good sign. So if we look at the view detail and open up this HTML file, so you can see that the distribution is random and the Moran size is very close to 0 and the p-value is not significant, because if you remember, the null hypothesis here states that the distribution is random, complete spatial random, CSR. But we couldn't reject that, right? Because the p-value is not significant. So the distribution is not significantly different from random distribution, which is a good sign for ordinary least square because their residuals should have a random distribution. And so let me close this. And another thing that ArcGIS gave us is, so we can map the residuals, as you can see. So here is the residuals that map. So how the question is how the residuals have been calculated. So the residuals are the difference between the outcome variable, which was the HIV prevalence, and the predicted variable based on those three variables, right? Limited, English, and so on. So if you open up the attribute table, so here is HIV prevalence, right? And also these are the variables that we had. So based on these three variables, we had it estimated the prevalence. So we have the HIV, the actual value, we have the estimated value. So the difference between actual and estimated value is residual, okay? So it's better that we have a lower residual, which means close to 0. But sometimes sometimes it may be over predicted or sometimes maybe under predicted. For example, if I select this blue area here, so in this blue area, so we have the actual value is 569, but it predicted 846. So the difference is very high. So it's over predicted in this area. Okay. So and also in some areas it's under predicted. So we don't have much like under prediction. Like if you can see here, we don't have like over 2.5 standard deviation. But these values that are close to 0, so these are much better because the value of the HIV prevalence and estimated are very close to each other, which means that the model did a very good job in these areas, right? But in these areas we have like over prediction or sometimes under prediction in some very few areas. But in general, the distribution looks random, which is good. If the distribution was clustered, which means that in some areas had very good fit or in some areas had very bad fit, so that's not a good model, okay? But here it seems a good model. It explains over 72 or 73% of the variation of the HIV prevalence, but one of the problems was the non-stationarity. So that's why we need the local models to model non-stationarity and also answer the second question, the local relationship between the variable and HIV prevalence. So to answer that, we're going to use a multi-scale geographically weighted regression. So the reason that I am using the MGWR is because it can capture spatial non-stationarity, and also I can estimate the local relationship between independent variables and dependent variable. All right, so where should I go? Analysis tab, tools, and here select MGWR, multi-scale geographically weighted regression, as you can see, which is a local form of linear regression that models spatial varying relationships. So I select this. So my input feature is going to be the HIV SVI, dependent variable is prevalence, and independent variable, I'm going to select the same variables, right? So I'm going to select the limited English, minority, and M units, right? And also, so since the variables are not in the same scale, so you can also standardize the variables or normalize the variable. As you can see, if you check it, the variables will be standardized using the z-score, which means that the difference between the variable minus the mean divided by a standard deviation. So the output feature, I'm going to I'm going to save this in this folder. I'm going to call this MGWR. So here is very important, neighborhood type. So how do you define the neighbors? Okay, so you can define it based on number of neighbors. So if you use the number of neighbors, as you can see, it's based on a specified number of closest neighbors for each feature. Okay, so for example, if the counties are densely packed, they are very close to each other, so the neighborhood will be smaller. Okay, but if the counties are more sparse, the neighborhood will be larger. So this approach is adaptive, and the size of the neighborhood adjusts based on density, so that for each location we will have a consistent number of the neighbors. And also you can define based on the distance, and if you define the neighborhood type based on distance band, it uses a constant and fixed distance around each feature. Okay, so this approach is not adaptive and maintains a consistent spatial extent. So I'm going to use the number of the neighbors for the neighborhood. So the next question is how many neighbors, right? Or what is the distance? In order to respond to this question, so we have a couple of options. You can use golden search, And golden search allows the software to find the optimal distance or optimal number of neighbors. And how this happens is that this method, based on the golden search, which is an iterative approach, searches for different number of the neighbors or different distances and selects the one that minimizes the AIC. So if you remember, I said that AIC, the lower AIC is better. So tries a variety of distances or tries a variety of number of neighbors and selects the one that minimizes the AIC. And gradient search, if you look at here, so gradient search is also another optimization algorithm that is iterative, but it moves toward the solution by making a small adjustment to minimize the AIC. And also you can have manual, interval, or user defined, which means that you specify a range of neighborhood size or you specify a range of distances, and the software will select the one that minimizes the AIC. So for the neighborhood type, for the neighborhood selection method, everything is based on minimizing the AIC because the lower AIC shows the most parsimonious model. So I'm going to use the golden search, which is a modern version. So I don't need to specify the minimum number of neighbors or maximum number of the neighbors. So let me HIV prevalence, and here was limited English, minority, and M-unit. Everything looks good, and then so I saved this as MGWR, which is fine, and then run. Okay, so now let's click on view details. First of all, it provided some summary of the coefficient estimate. It provides that the mean, standard deviation, mean, minimum, median, maximum, but the variables has been scaled based on the z-score, if you remember, right? And also, if you look at the adjusted R-square compared to the ordinalist square, so you can see that adjusted R-square is higher. So the other one, OLS, I think was 72%, right? So 72 something, so almost 5% increase in explaining the HIV prevalence, right, with the same variables. And also if you look at the AIC, corrected AIC, I think the other one was 500 something, right? But now it's 77, which shows that it's much more parsimonious model, right? Compared to the OLS model. So also this table shows how many neighbors or how many counties and what percentage of them were used for each variable. Okay, so for example, for limited English, the total number was 46, right? 30 out of 46 variables were used for the neighbor for each location, and which is 65% of the neighbors for each location. But for the minority and for the M unit, all of them have been selected. As you can see, it has used different scale, so that's why this is called a multi-scale model. So if you use the GWR, not multi-scale GWR, all of them, they use the same number of the neighbor for all of the variable. But for MGWR, it uses different number of the neighbors for each variable. So this one, limited English, has more localized influence. Okay, but minority and M unit, they seem like global influence. And also we have another column, significance. So it shows that, so among the number of the counties that you have, how many of them were significant? Okay, so for example, for intercept, none of them were significant, but for limited English, 21 out of 46, 45 of them were significant. But for minority, all of them had a significant impact, but M unit, almost 97% of them. So that we will also see that in the map. And here also based on the iteration, as I mentioned, so the golden search is an iterative process and selects the one that has the lowest AIC. Okay, so for example, here you can see the AIC was lowest, and here, as you can see, AIC, and here you can see how many neighbors, for example, for intercept, for limited English, for minority, and M units. So to better understand the results, so let's look at the maps. Okay, so I am going to close this and also close this one. So the first map that I have is residuals, of the MGWR. So if you open up that and go to the very right end, so we have, so this is very important. So we have the residuals that are scaled. So the lower residual is better. Okay, so if I, for example, sort that, so here I have higher residual, I think this one. So this is like, this is not a good fit for this county. So the difference between the estimated and actual value is higher. So again, you can run the global Moran's eye based on the residual or standard residual, but if you check that, you can see that the distribution, you can tell that the distribution is kind of random. It's not a cluster distribution, right? So the next map is, for example, for the limited English, right? So this one, let me make sure that this is the map that I'm looking for. Yeah. So this is for the limited English. As you can see, as I mentioned, so some of them were not significant. So you can here see that. So these counties didn't have a significant impact on the HIV prevalence, right? And also here you can see that the impact of the limited English on the HIV prevalence in these areas is different from these areas. Okay, so based on this location, so it has more impact on these areas compared to these areas. So it shows the local influence of the variables on the HIV prevalence, right? But I don't think for the other variables, for example, for the minority, so it has kind of global impact, right? So none of them were not significant. All of the counties were significant, 100% of them. And the impact is between 0 to 0.38. So it has a consistent impact on the HIV prevalence. But how about if I look at the EP minority, M unit, sorry. So for the M units, you can see only like a few of them, right? So if you remember, 97% something were significant, but only a few of them were not significant. And the impact is almost consistent across the South Carolina, but in some areas had higher impact. M unit has higher impact on the HIV prevalence. And also if you look at the intercept, so here, let me remove this. So for the intercept, as you can see, it had a no impact, no significant impact on the HIV prevalence in none of the counties of the South Carolina. So and the final thing is, if you look at again to the attribute table of the residuals, open up the attribute table. So there was a field, I think was cookD and also influence. So what is cookD or cook distance? It is used to identify the influential data points, okay, that have large impact on the fitted model. Okay, so sometimes it is useful to identify potential outlier that can distort the result, especially if you have a large data set, so that you want to see which location or which data point can significantly impact the result. So sometimes you may need to remove it from your data set. So in general, if cookD is greater than 1, it is considered highly influential. So let's look at our data. So if you sort the data, so the largest one is 0.61 and the smallest is almost 0. So we don't have any influential data compared to the other data in this data set, okay? And also, if you look at the condition number, so condition number, it is used for to evaluate multicollinearity, okay? So if you have low condition number close to 1, so it shows that their collinearity is very low, which is okay. But if you have condition number 30, 100, so it shows that variables are highly correlated or redundant. Okay, so if I select, for example, you can see that the largest condition number is 3, which is close to 1. And so multicollinearity for the location, because it's for each location, so multicollinearity is not a problem